The topic for today's module is Subrings and Ideals. Dear learners, today we are going to learn about subrings and ideals in ring theory. Let us see the definition of subrings. Let R be a ring and S be a subset of R. We say that S is a subring of R if S becomes a ring with the induced addition and multiplication. Next is the definition of a center. The center of a ring R is the collection of all elements of the ring R that commute with every element, that is Z equal to set of all Z such that A Z equal to ZA for all A belongs to R. The center of a ring is a subring containing together with every invertible element its inverse. There is some simplest test for subring is as follows. A non-empty subset S of a ring R is a subring if S is closed under subtraction and multiplication. That is, if A minus B and AB are in S, whenever A and B are in S. Proof is, in previous subgroup module, we have seen that the subset S is an abelian group under addition. Also, since multiplication in R is associative as well as distributive over addition, the same is true for multiplication in S. Thus, the only condition remaining to check is that multiplication is a binary operation on S. But this is exactly what closure means. We leave it to the student to check that each of the following examples is a subring. Examples: the set of even integers 2Z is a subring of Z. The integers Z is a subring of Q. The rational numbers Q is a subring of R. The real numbers R is a subring of the complex numbers C. The set of all matrices of the form A0, 0, 0 is a subring of M2 of R. The set of all matrices A0, 0B such that A, B belongs to Z of diagonal matrices is a subring of the ring of all 2 by 2 matrices over Z. Singleton 0 and R are subrings of any ring R. They are called the trivial subrings of R. Set of all 0, 2, 4 is a subring of the ring Z6, the integers modulo 6. For each positive integer n, the set n is equal to set of all 0 plus or minus n plus or minus 2n plus or minus 3n etc. is a subring of the integers Z. Let x equal to set of all a plus b row 2 such that A, B belongs to Q. Then x is a subring of R. Consider the subset y equal to set of all 0, 2. Then y is a subring of Z4. Consider the Gaussian integers defined as all complex numbers of the form a plus bi, where a and b are integers. Then the Gaussian integers form a subring of the complex numbers. Let x any set and let F be the set of all finite subsets of x. Then F is a subring of row of x delta intersection. Consider the set S equal to set of all a by 2 power r such that a, r belongs to Z and r greater than or equal to 0. Then S is a subring of the rational numbers Q. Let R be the ring of all real valued functions of a single real variable under pointwise addition and multiplication. The subset S of R of functions whose graphs pass through the origin form a subring of R. Let us see some elementary properties of subrings. A non-empty subset S of a ring R is a subring if and only if A and B belongs to S and AB belongs to S. The intersection of two subrings of a ring R is a subring of R. The union of two subrings of a ring need not be a subring. The union of two subrings of a ring is again a subring if and only if one is contained in the other. Let us discuss about the another concept of ideals. Let us start with an introduction of ideals. In ring theory, a branch of abstract algebra, an ideal is a special subset of a ring. Ideals generalize certain subsets of the integers such as the even numbers or the multiples of 3. Addition and subtraction of even numbers preserves evenness, and multiplying an even number by any other integer results in another even number. These closure and absorption properties are the defining properties of an ideal. An ideal can be used to construct a quotient ring similarly to the way that in group theory, a normal subgroup can be used to construct a quotient group. Among the integers, the ideals correspond one for one with the non-negative integers. In ring theory, every ideal is a principal ideal consisting of the multiples of a single non-negative number. However, in other rings, the ideals may be distinct from the ring elements, and certain properties of integers, when generalized to rings, attach more naturally to the ideals than to the elements of the ring. For instance, the prime ideals of a ring are analogous to prime numbers, and the Chinese remainder theorem can be generalized to ideals. There is a version of unique prime factorization for the ideals of a Dedekind domain, that is a type of a ring important in number theory. The concept of an order ideal in order theory is derived from the notion of ideal in ring theory. A fractional ideal is a generalization of an ideal, and the usual ideals are sometimes called integral ideals for clarity. Ideals were first proposed by Richard Dedekind in 1876. There were a generalization of the concept of ideal numbers developed by Ernst Kummer. Later, the concept was expanded by David Hilbert and especially Emmy Noether. Let us see the definition of an ideal. For an arbitrary ring R, plus, dot, let R, plus be its additive group. A subset I is called a left ideal if it is an additive subgroup of R that absorbs multiplication from the left by elements of R. That is, I is a left ideal if it satisfies the following two conditions. I, plus is a subgroup of R, plus. For every R belongs to R and every X belongs to I, the product Rx belongs to I. A right ideal is defined with the condition Rx belongs to I replaced by Xr belongs to I. A two-sided ideal is a left ideal that is also a right ideal and is sometimes simply called an ideal. When R is a commutative ring, the definitions of left, right and two-sided ideal coincide, and the term ideal is used alone. Ideals I of a ring R are in some sense a generalization of the set of multiples of an integer. That is, Nz is a subset of Z. Intuitively, the definition can be motivated as follows. Suppose we have a subset of a ring and that we would like to obtain a ring with the same structure as R, except that the elements of S should be 0. They are in some sense negligible. But if S1 equal to 0 and S2 equal to 0 in our new ring, then surely S1 plus S2 should be 0 too, and RS1 as well as RS2 should be 0 for any element R belongs to R. It is 0 or not. The definition of an ideal is such that the ideal I generated by S is exactly the set of elements that are forced to become S0 if becomes 0 and the quotient ring R by I is the desired ring where S is 0 and only elements that are forced by S to be 0 are 0. The requirement that R and R by I should have the same structure except that I becomes 0 is formalized by the condition that the projection from R to is a surjective ring homomorphism R by I. The quintessential example is when R equal to Z and S equal to singleton n for some non-zero n belongs to Z. By considering n to be 0, we are essentially reducing elements of Z to their remainder after dividing by n. Thus, I equal to nz equal to set of all etc. minus 2n minus n 0 n 2n etc. and R by I equal to Z by nz equal to Zn is the set of possible remainders after dividing an integer by n. That is the cyclic group of order n. In the language of module theory, a left, respectively right, two-sided ideal is precisely a left, respectively right, or two-sided R submodule of R. That is to say, a left ideal, for example, is an additive subgroup that is stable under the left multiplications by the elements of R. Next one is ideal test in practice. One can easily identify that ideals test, which is an immediate consequences of the definition of ideal. The first theorem is a non-empty subset A of a ring R is an ideal of R if AB belongs to A whenever A, B belongs to A. RA and R are in A whenever A belongs to A and R belongs to R. Let us look some of examples of ideals. For any ring R, singleton 0 and R are ideals of R. The ideal singleton 0 is called the trivial ideal. The even integers form an ideal in the ring Z of all integers. It is usually denoted by 2Z. This is because the sum of any even integers is even and the product of any integer with an even integer is also even. Similarly, the set of all integers divisible by a fixed integer n is an ideal denoted by nz. The set of all polynomials with real coefficients which are divisible by the polynomial x square plus 1 is an ideal in the ring of all polynomials. Let R of x denote the set of all polynomials with real coefficients and let A denote the subsets of all polynomials with constant term 0. Then A is an ideal of R of x and A equal to ideal generated by x. The set of all n by n matrices whose last row is 0 forms a right ideal in the ring of all n by n matrices. It is not a left ideal. The set of all n by n matrices whose last column is 0 forms a left ideal but not a right ideal. The ring C of R of all continuous functions f from R to R under pointwise multiplication contains the ideal of all continuous functions f such that f of 1 equal to 0. Another ideal in C of R is given by those functions which vanish for large enough arguments. That is, those continuous functions f for which there exists a number L greater than 0 such that f of x equal to 0 whenever modulus of x greater than L. Let Z of x denote the ring of all polynomials with integer coefficients, and let I be the subset of z of x of all polynomials with even constant term. Then I is an ideal of z of x and I equal to ideal generated by x comma 2. For the sake of succinctness, some results are stated only for left ideals but are usually also true for right ideals with appropriate notation changes. In a ring R, the set R itself forms a two-sided ideal of R called the unit ideal. It is often also denoted by ideal generated by 1 since it is precisely the two-sided ideal generated by the identity 1R. Also, the set 0R consisting of only the additive identity 0R forms the two-sided ideal called the 0 ideal and is denoted by ideal generated by 0. Every left, right or two-sided ideal contains the 0 ideal and is contained in the unit ideal. A left, right or two-sided ideal that is not the unit ideal is called a proper ideal, as it is a proper subset. Note, a left ideal I is a proper if and only if it does not contain a unit element. Since if U belongs to I is a unit element, then R equal to R U inverse into U belongs to I for every R belongs to R. Typically, there are plenty of proper ideals. A ring is called a simple ring if it is non-zero and has no two-sided ideals other than ideal generated by 0 and ideal generated by 1. Thus, a skew field is a simple and a simple commutative ring is a field. The matrix ring over a skew field is a simple ring. If F from R to S is a ring homomorphism, then the kernel of F equal to F inverse of 0S is a two-sided ideal of R. By F of 1R equal to 1S convention, and thus if S not equal to 0, then kernel of F is a proper ideal. More generally, for each left ideal I of S, the pre-image F inverse of I is a left ideal. If I is a left ideal of R, then F of I is a left ideal of the subring F of R of S. Unless F is surjective, F of I need not be an ideal of S. Ideal correspondence. Given a surjective ring homomorphism F from R to S, there is a bijective order preserving correspondence between the left, respectively right, two-sided ideals of R containing the kernel of F and the left, respectively right, two-sided ideals of S. The correspondence is given by I to F of I and the pre-image J to F inverse of J. A left, respectively right, two-sided ideal generated by a single element x is called a principal left, respectively right, two-sided ideal generated by x and is denoted by Rx, respectively xr, or xr. The principal two-sided ideal Rxr is often also denoted by ideal generated by x. If x equal to set of all x1, x2, etc. xn is a finite set, then R cross R is also written as ideal generated by x1, x2, etc. xn. In the ring of integers, every ideal can be generated by a single number, so is a principal ideal domain. As a consequence of Euclidean division or some other way, there is a bijective correspondence between ideals and congruence relation, equivalence relation that respect the ring structure on the ring. Given an ideal I of a ring R, let x tilde y if x minus y belongs to I. Then tilde is a congruence relation on R. Conversely, given a congruence relation tilde on R, let I equal to set of all x such that x tilde 0. Then I is an ideal of R. Here different types of ideals are studied because they can be used to construct different types of factor rings. First one is maximal ideal. A proper ideal I is called a maximal ideal if there exists no other proper ideal J with I a proper subset of J. The factor ring of a maximal ideal is a simple ring in general and is a field for commutative rings. Next one is minimal ideal. A non-zero ideal is called minimal if it contains no other non-zero ideal. Next is prime ideal. A proper ideal I is called a prime ideal if for any A and B in R, if AB is in I, then at least one of A and B is in I. The factor ring of a prime ideal is a prime ring in general and is an integral domain for commutative rings. Next is radical ideal or semi-prime ideal. A proper ideal I is called a radical or semi-prime if for any A in R, if A power n is in I for some n, then A is in I. The factor ring of a radical ideal is a semi-prime ring for general rings and is a reduced ring for commutative rings. Next is primary ideal. An ideal I is called a primary ideal if for all A and B in R, if AB is in I, then at least one of A and B power n is in I for some natural number n. Every prime ideal is primary but not conversely. A semi-prime primary ideal is prime. Principal ideal. An ideal generated by one element. Finitely generated ideal. This type of ideal is finitely generated as a module. Primitive ideal. A left primitive ideal is the annihilator of a simple left module. Irreducible ideal. An ideal I is said to be irreducible if it cannot be written as an intersection of ideals which properly contains I. Co-maximal ideals. Two ideals I and J are said to be co-maximal if x plus y equal to 1 for some x belongs to I and y belongs to J, that is I plus J equal to R. Nil ideal. An ideal is a nil ideal if each of its elements is nilpotent. Nilpotent ideal. Some power of it is 0. Parameter ideal. An ideal generated by a system of parameters. Two other important terms using ideal are not always ideal of the ring. Fractional ideal. This is usually defined when R is a commutative domain with quotient field K. Despite their names, fractional ideals are R submodules of K with a special property. If the fractional ideal is contained entirely in R, then it is truly an ideal of R. Invertible ideal. Usually, an invertible ideal A is defined as a fractional ideal for which there is another fractional ideal B such that AB equal to BA equal to R. Some authors may also apply invertible ideal to ordinary ring ideals A and B with AB equal to BA equal to R in rings other than domains. We can form a ring based on the ideals. We have already discussed briefly about that ring in previous module, which is nothing but a quotient ring or factor ring. Let us recall it once again here. Factor rings. Let R be a ring and I an ideal of R. Since R is a group under addition and I is a normal subgroup of R, we may form the factor group R by I equal to set of all R plus I such that R belongs to R. The natural question at this point is, how may we form a ring of this group of cosets? The addition is already taken care of, and by analogy with groups of cosets, we define the product of two cosets A plus I and B plus I as AB plus I. Next we are going to see the existence of factor rings theorem. Statement is, let R be a ring and A be a subring of R. The set of cosets, set of all R plus A such that R belongs to R is a ring under the operations S plus A plus T plus A equal to S plus T plus A and S plus A into T plus A equal to ST plus A if and only if A is an ideal of R. We go through the proof. We do know that the set of cosets form a group under addition, and it is trivial to check that the multiplication is associative and that multiplication is distributive over addition. Once we know that multiplication is indeed a binary operation on the set of cosets. Hence, the proof boils down to showing that multiplication is well defined if and only if A is an ideal of R. To do this, let us suppose A is an ideal and let S plus A equal to S dash plus A and T plus A equal to T dash plus A. Then we must show that ST plus A equal to S dash T dash plus A. Well, by definition, S equal to S dash plus A and T equal to T dash plus B, where A and B belongs to A. Then ST equal to S dash plus A into T dash plus B, that is equal to S dash T dash plus A T dash plus S dash B plus AB. And so, ST plus A equal to S dash T dash plus A T dash plus S dash B plus AB plus A, that is equal to S dash T dash plus A. Since A absorbs the last three summands of the middle expression, thus multiplication is well defined when A is an ideal. On the other hand, suppose A is not an ideal of R, then there exist elements A belongs to A and R belongs to R such that AR does not belongs to A and RA does not belongs to A. For convenience, say AR does not belongs to A. Consider the elements A plus capital A equal to 0 plus A and R plus A. Clearly, A plus A into R plus A equal to AR plus A, but 0 plus A into R plus A equal to 0 into R plus A, that is equal to A. Since AR plus A not equal to A, the multiplication is not well defined and the set of cosets is not a ring. Let's look at few factor rings. The first example is, consider the factor ring Z by 4Z equal to set of all 0 plus 4Z, 1 plus 4Z, 2 plus 4Z, 3 plus 4Z. To see how to add and multiply, consider 2 plus 4Z and 3 plus 4Z. 2 plus 4Z plus 3 plus 4Z equal to 5 plus 4Z, that is equal to 1 plus 4 plus 4Z, that is equal to 1 plus 4Z. 2 plus 4z into 3 plus 4z equal to 6 plus 4z, that is equal to 2 plus 4 plus 4z, that is equal to 2 plus 4z. One can readily see that the two operations are essentially modulo 4 arithmetic. Thus, z by 4z is isomorphic to z4. The second example is the factoring 2z by 6z equal to set of all 0 plus 6z, 2 plus 6z, 4 plus 6z. Here the operations are essentially modulo 6 arithmetic and the ring is isomorphic to Z3. Here is a non-commutative example of an ideal and factoring. Example 3 is, let R equal to set of all A1, A2, A3, A4 such that AI belongs to Z and let I be the subset of R consisting of matrices with even entries. It is easy to show that I is indeed an ideal of R. Consider the factoring R by I. The interesting question about this ring is its size. Just what is it? We claim it is 16. In fact, R by I equal to set of all 2 by 2 matrices R1, R2, R3, R4 plus I such that Ri belongs to set of all 0, 1. An example illustrates the typical situation which of 16 elements is 7, 8, 5 minus 3 plus I. Well, observe that 7, 8, 5 minus 3 plus I equal to 1, 0, 1, 1 plus 6, 8, 4 minus 4 plus I equal to 1, 0, 1, 1 plus I. Since an ideal absorbs its own elements. In this session, we had discussed about subrings and subring test with examples. In addition to that, we had seen some of its properties too. After that, we had seen about ideals and ideal test. Finally, we seen the quotient ring with example. I hope you got the concepts very well. We will meet in the next session. Thank you.